What if I told you that the universe has a memory limit? Not a practical limit, a hard mathematical ceiling on how much information can exist. What if the heat you feel on a summer day isn't just solar radiation, but the thermodynamic exhaust of reality itself, computing its own future? For over a century, physicists believed the universe was continuous, infinitely divisible, smooth, deterministic. But something changed. Quantum mechanics, black hole thermodynamics, and information theory collided, forcing us to confront a radical possibility. Reality isn't a collection of particles and fields, it's information. Pure computational information, constrained by rigid thermodynamic bounds. At the heart of this revolution is an unlikely connection: cryptographic hash functions. You know, the algorithms that secure your passwords and verify blockchain transactions. These mathematical structures take unlimited inputs and compress them into a fixed, finite output space. And their behavior, deterministic, irreversible, pseudo-random, mirrors the fundamental laws of physics with uncanny precision. So we have to ask, does the universe contain only a finite number of possible futures? Is the arrow of time just information being deleted? In black holes, does information truly vanish, a cosmic hash collision, or does it merely get encrypted beyond any hope of recovery? And the question that haunts every physicist who goes down this rabbit hole: if the universe operates like a computer, are we living inside a simulation? Let me show you how deep this goes. In 1981, a physicist named Jacob Bekenstein proved something extraordinary. He showed that any finite region of space, containing a finite amount of energy, can only hold a finite amount of information. Not a lot of information, not more information than we can measure. Finite. There's an absolute upper limit. The math is surprisingly elegant. The maximum entropy, maximum information, in a spherical region is proportional to its surface area times its energy content divided by the Planck scale. What this means is profound. You cannot pack infinite information into a finite volume. The universe has a file size limit. Think of it like this. If you wanted to perfectly describe every quantum state in a region of space, every particle position, every momentum, every field fluctuation, you'd need a certain number of bits. Bekenstein proved that number is bounded. For our observable universe, current estimates put the total information capacity somewhere between 10 to the 90th and 10 to the 120th bits. Now, that number is incomprehensibly large. But it's not infinite, and that changes everything. See, in classical physics, we imagined a continuum. Smooth, infinitely divisible space and time. Infinite possible configurations. But Bekenstein's bound says no. The universe can only occupy a massive, but ultimately finite, number of distinct quantum states. It's not a smooth film, it's a finite state machine, pixelated at scales far beyond our perception, but pixelated nonetheless. This means the future of the universe isn't a branching tree of infinite possibilities, it's a vast but finite maze. Every Planck time, the universe transitions from one state to another, and there are only so many rooms in this maze. Combinatorially, it's so large it creates the illusion of continuous choice, like how individual pixels disappear when you step back from a 4K screen. But fundamentally, reality is discrete. And here's where it gets strange. If the total number of states is finite, the universe's trajectory through time must eventually either terminate or loop. It cannot explore infinite novelty forever. The clock is running on a bounded tape. Now you might be thinking, okay, but this is theoretical. Surely quantum field theory with its infinite degrees of freedom breaks this. No. Physicist Horacio Cassini proved that when you properly define entropy as the difference between excited states and the vacuum, all those ultraviolet infinities vanish. Even at the quantum field level, information density is bounded. The universe has a maximum hard drive capacity, and right now, It's running the most complex computation imaginable, the unfolding of time itself. But how does that computation actually work? Let me show you something. I'm going to hash a simple word. Hello. The output is this 64-character string of hexadecimal gibberish. Now watch what happens when I change just one letter. Hello, with a W at the end. The entire hash exploded. Over 50% of the bits flipped. This is called the avalanche effect. A tiny change in the input cascades through the algorithm, producing an output that looks completely unrelated. It appears random, but here's the key: it's not random. It's 100% deterministic. SHA-256 is a cryptographic hash function. It takes an unlimited number of possible inputs and maps them to exactly 2 to the 256th possible outputs. That's a many-to-one function. Billions of different inputs could theoretically produce the same hash. When that happens, it's called a hash collision. And here's the crucial part. If you only see the output, the hash, you cannot reconstruct the input. The specific path backward has been mathematically deleted. Now, why am I talking about password algorithms in a video about the universe? Because the behavior of hash functions, deterministic chaos, pseudo-randomness, irreversible compression, is identical to how physical reality operates. Physicist Stephen Wolfram calls this computational irreducibility. Even if a system follows simple, deterministic rules, the complexity explodes so fast that there's no shortcut to predict the outcome. The only way to know the future is to run the simulation step by step. You can't skip ahead, you have to compute it. This is why weather is unpredictable beyond a few days. This is why turbulent fluids are chaotic. Not because the laws are random, the Navier-Stokes equations are completely deterministic, but because the computational depth is so immense that prediction becomes impossible. The universe doesn't need fundamental randomness. Deterministic depth is indistinguishable from randomness to any observer without the key. In 2026, researcher Dean Kulik proposed something radical and highly speculative: the nexus framework. It's a fringe theory that suggests SHA-256 might be more than just analogous to physics. Kulik argues it could be a literal universal instruction set, with all physical change reducing to 10 fundamental operations: copy, combine, split, transform, permute, compare, select, iterate, hash, prove. Now, this isn't mainstream physics. It's more of a thought experiment. But it captures something real: the structural similarity between cryptographic processes and physical laws. Setting aside Kulik's specific claims, here's what we can say. The universe does seem to take its current state and generate the next through rule-based transformations. And if those transformations are many-to-one, mapping multiple possible pasts to the same present, then the computational metaphor has real explanatory power. The future is deterministic. But the past is ambiguous, which brings us to a strange question. If the universe is constantly compressing information, deleting historical pathways to fit within its finite state space, what happens to all that deleted data? Look at the thermal signature of a coffee cup, a human hand, a computer processor under load, all glowing with infrared radiation. Heat. We're so familiar with it that we forget how strange it is. Where does heat come from? Sure, you can say molecular motion or kinetic energy, but that just pushes the question back. Why does erasing information, compressing data, or computing anything at all generate warmth? In 1961, physicist Rolf Landauer proved something remarkable. He showed that information isn't just an abstract concept, it's deeply, fundamentally physical. And any time you irreversibly manipulate information, there's a thermodynamic cost. The principle is simple. Erasing one bit of information requires a minimum energy expenditure of kT times the natural log of 2, where K is Boltzmann's constant and T is temperature. that energy doesn't disappear. It becomes heat, dissipated into the environment. Think about what this means. Every time a computer overwrites memory, it generates heat. Not because of inefficient circuits, that's engineering overhead. Even a perfectly ideal computer operating at the thermodynamic limit must generate heat when it erases data. Information erasure and thermal exhaust are two sides of the same coin. Now, here's where things get interpretive. The universe's state space is finite, bounded by Bekenstein. It cannot store a complete record of every microscopic interaction. To keep computing forward, to generate new moments, it must continuously overwrite old data through coarse graining. If we take Landauer's principle seriously and extend it cosmically, and this is one interpretation, not settled physics, then this erasure generates heat. So one way to think about ambient thermal energy, it's the exhaust of the universe processing information, reality computing itself. But wait, if that's the case, why is winter colder than summer? If the universe is computing everywhere all the time, shouldn't heat be constant? Here's one way to conceptualize it, treating Earth as an open computational node. The Sun transmits low-entropy photons carrying structured electromagnetic information. Earth receives this energy and processes it through weather, photosynthesis, chemical reactions. During summer, the hemisphere tilts toward the Sun, receiving maximum solar energy. More energy input means more thermodynamic processes, more irreversible state changes, more Landauer erasure, more heat output. In winter, the tilt reduces energy input. Fewer photons, less processing, less heat output. It's a geometric effect on energy flow. Now, is this literally computational throughput? That's interpretive, but it shows how information theoretic thinking can provide new perspectives on familiar phenomena. Winter is colder because Earth's local computation rate has dropped. The heat we feel is information being deleted, and when less information needs deleting, there's less heat. But if the universe is so careful about information, protecting it through thermodynamic constraints and computational rules, what happens in the most extreme environment imaginable? What happens when information falls into a black hole? This is the first direct image of a black hole's event horizon. A boundary in space-time so extreme that nothing, not matter, not light, not information, can escape once it crosses that threshold. Or can it? In the 1970s, Stephen Hawking applied quantum mechanics to curved space-time around black holes and discovered something shocking. Black holes aren't completely black. They emit faint thermal radiation. Quantum fluctuations at the event horizon cause particle-antiparticle pairs to spontaneously appear. One particle falls in, the other escapes. Over immense timescales, the black hole evaporates. This radiation carries energy away, so the black hole slowly loses mass. Eventually, it disappears entirely. But here's the problem. Hawking calculated that this radiation is perfectly thermal. It's featureless. It depends only on the black hole's mass, charge, and spin, nothing else. Imagine you throw an encyclopedia and a block of lead into a black hole. Same mass, wildly different information content. According to Hawking's original calculation, they both produce the exact same amorphous cloud of thermal photons as the black hole evaporates. Two distinct initial states, one final state, a many-to-one mapping, a hash collision. If this is true, if the information about what fell in is genuinely destroyed, then quantum mechanics is wrong. Not incomplete. Wrong. See, quantum mechanics is built on a principle called unitarity. It says that the evolution of a quantum system is always reversible. If you know the final state perfectly, you can mathematically reconstruct the initial state. Information is never lost. It might get scrambled, entangled, or spread out, but it's always recoverable in principle. A unitary transformation is like a perfect encryption algorithm. The information is still there, just encoded. But if a black hole truly destroys information, that's not encryption. That's deletion, and deletion breaks unitarity. For decades, this paradox tore theoretical physics apart, Some argued we needed to abandon quantum mechanics. Others said general relativity must be wrong near singularities. It became one of the deepest problems in all of science. And in recent years, a leading resolution has emerged, though the debate is far from settled. Physicist Don Page predicted that if information is preserved, the entropy of Hawking radiation should follow a specific curve. Early in the evaporation process, entropy increases as expected. But at the Page time, roughly halfway through the black hole's lifetime, something dramatic should happen. The entropy stops rising and begins to fall. The radiation would start becoming correlated with what fell in. Not obviously. You can't read the encyclopedia by analyzing individual photons. But the quantum entanglement structure changes. The information is there, just insanely scrambled. Recent breakthrough calculations using something called replica wormholes and the ADS-CFT correspondence have successfully reproduced this Page curve mathematically. The math is brutally complex, but the results suggest black holes do not execute true hash collisions. They appear to be unitary encryption devices. If this interpretation is correct, and many leading physicists now believe it is, then an observer with a sufficiently powerful quantum computer could, in principle, capture all the Hawking radiation, reverse the unitary transformations, and reconstruct everything that fell in. The scrambling is computationally irreducible, but it's not destruction. This suggests nature fiercely protects unitarity. Even at the edge of a singularity, information survives, encrypted, smeared across subtle quantum correlations, practically irrecoverable, but not deleted. The universe allows many-to-one mappings at the macroscopic level. That's how time's arrow emerges from coarse graining. But at the fundamental quantum level, it enforces one-to-one transformations. Every microstate maps to exactly one future microstate. No true hash collisions exist in nature. So the universe operates with finite state space. It processes information through deterministic chaos that looks like cryptographic hashing. It generates thermodynamic exhaust as it erases macroscopic data. And it fiercely protects quantum information from true destruction. If it looks like a computer, acts like a computer, and heats up like a computer, are we living in a simulation? The simulation hypothesis is seductive. If the universe has finite information capacity, dissipates computational heat, and operates through algorithmic-like processes, maybe it's literally a program running on some higher-dimensional supercomputer. But there's a fascinating mathematical argument against this. Whether it's definitive is still debated, but it's worth considering. In 1931, mathematician Kurt Gödel proved something devastating about formal systems. He showed that any sufficiently complex logical system contains true statements that cannot be proven within that system's rules. These are called Gödelian truths, propositions that are undeniably true but algorithmically undecidable. The classic example: this statement cannot be proven. If you could prove it, it would be false, but if you can't prove it, then it's true, and your system is incomplete. There's truth outside the reach of your algorithms. Here's the argument. Any computer, classical or quantum, regardless of how powerful, operates algorithmically. It follows programmed logic. But Gödelian truths are, by definition, not computable. No algorithm can fully capture them. Tarski showed that truth itself cannot be fully defined within any formal language. Chaitin demonstrated that most mathematical facts are random and incompressible, true for no reason that any algorithm can derive. In 2025, researchers Mir Faisal and Lawrence Krauss published a mathematical argument suggesting that a complete theory of quantum gravity, explaining how space-time emerges, cannot be fully algorithmic. If space-time is emergent from deeper quantum information, and that emergence involves Gödelian truths, aspects that are true but unprovable, then describing this process requires something beyond computation. The researchers call this non-algorithmic understanding. It's controversial, and not all physicists agree. But if they're right, then because any simulation must be algorithmic by definition, The universe's foundations transcend what any program could replicate. You could simulate aspects of the universe, quantum mechanics, particle physics, cosmology. But you couldn't simulate the totality of reality, including its own emergence from mathematical principles, because that process would exceed algorithmic logic. So one interpretation. The universe uses computational mechanics but has non-algorithmic foundations. The universe computes. But it is not a computation. So we're left with something beautiful and strange. Reality operates at the intersection of rigid mathematical law and irreducible complexity. It's deterministic, yet unpredictable. Finite yet vast. Computational in its mechanics but transcendent in its foundations. We exist inside something that thinks like a machine but dreams in Gödelian truths. And that brings us full circle. Let's pull it all together and be clear about what's established physics versus interpretation. The universe has a finite information capacity. That's the Bekenstein Bound. Proven, mathematical, not controversial. There are only so many possible quantum states, vast beyond comprehension, but ultimately countable. As the universe evolves, it follows deterministic laws that generate computational irreducibility. Prediction becomes impossible without living through each moment. That's Wolfram's observation, well supported across physics, from weather to quantum mechanics. Through coarse graining and macroscopic observation, many possible microscopic pasts map to the same present. This many-to-one structure isn't controversial. It's how statistical mechanics works. And it creates time's arrow through entropy increase. Landauer's principle is proven. Erasing information generates heat. That's not debatable. What's interpretive is extending this to say all heat is computational exhaust of the universe processing itself. That's one framework. Elegant, but not settled science. The black hole information paradox? Recent calculations suggest information survives, encrypted in Hawking radiation. The page curve has been reproduced mathematically. But the debate isn't over. This is a leading theory, not proven fact. And whether the universe transcends simulation through Gödelian incompleteness. That's a fascinating mathematical argument, but it's contested. Some find it compelling, others unconvincing. What we can say with confidence, reality operates with information theoretic constraints we're only beginning to understand. The computational metaphor reveals deep patterns, but whether the universe literally computes or just behaves as if it does, that's still an open question. One way to see it: every photon from the sun carries energy. Every chemical reaction follows thermodynamic laws. Every breath you take involves irreversible physical processes. Whether you call that computation or not, there's something profound about viewing reality through an information theoretic lens. The universe might be a hash function, or it might just look like one from where we stand. So what do you think? Is time really just deleted information? Does the warmth you feel prove the universe is computing? If you want to dig deeper, I've linked the original research papers in the description. And if this broke your brain in the best possible way, subscribe, because we're just getting started exploring the computational nature of reality. Thanks for watching.